Hi, welcome to part 2 of our lecture on stars. In this part of the lecture, we will look at how stars are classified. Let's start with the discussion of the distance to the stars. How far away are the stars, and how do we measure cosmic distances? We learned about the astronomical unit earlier in this course when we studied Kepler's laws. So remember the idea that for studying cosmic distances, units like inches or meters or even miles are much too small. They're too small to be practical for measuring cosmic distances. So in astronomy, we often measure distances using different units that are more appropriate. And one of those distances is the AU, or astronomical unit, which is defined as the distance between the Earth and the Sun, which, by the way, is about 93 million miles. Now, there's even a better distance indicator for measuring distances to stars, and that is the distance of unit of distance called the light year. So remember that the speed of light is given by the letter c, and it's 3 times 10 to the 8th meters per second, or 186,000 miles per second. So 1 light year, or Ly, is the distance that light travels in 1 year. So a light year is not a unit of time, it's a unit of distance. So imagine taking a flashlight and pointing it up at the sky, and on New Year's Day you turn on this flashlight. So this beam comes shooting out of your flashlight at the speed of light. It's traveling 186,000 miles every second. Well, after precisely 1 year, okay, so at the end of December and January 1st on the next year, this beam has now traveled 1 light year. So 1 light year turns out to be almost 6 trillion miles. Or it's about 60,000 astronomical units. So a light year is obviously an enormously large distance. It's almost incomprehensible to think how big 6 trillion miles really is. But when we talk about distances in the universe, we will be using the distance unit of the light year. Just to give you a sense of scale of how big 1 light year is, what is the number 6 trillion? So a light year, remember, is 6 trillion miles. So 6 trillion is a 6 with 12 zeros after it. So that's 6 times 10 to the 12th. It's approximately equal to the number of sand grains in 15 dump trucks. So, this would, obviously it would be a futile task to try to count all these sand grains, but that is the approximate number that is close to 6 trillion. Now, getting back to the distance to the stars, one of the earliest methods that was used to figure out how far the stars was is a method that was familiar to surveyors. It's called triangulation. So for example, let's say you're hiking along here and you come across this river here, and on the other side of the river, far away, is a tree, and you're wondering how far away is this tree from you. So you don't want to get wet or risk swimming across this river. So what you do is you use a little bit of math and trigonometry to figure out the distance. What you can do is you can start here at point A and measure this distance here to point B, which is called a baseline. And then from this point A, measure the angle here between the baseline and the line of sight to the tree. So let's say here in this example, it's 66 degrees. Then we walk over here to point B and we measure the angle here between the baseline and this line of sight to the tree. And let's say that angle is 71 degrees. So now what we can do, and we're actually not going to do the math in this class, so don't worry about it, but by doing some trigonometry using sines and cosines and so forth, it's relatively simple to figure out the height of this triangle, which tells us the distance to the tree. So triangulation basically provides an indirect way to measure the distance to something. So what does this have to do with astronomy? Well, astronomers use a similar analogous method called parallax to find the distance to stars. So here's something you can do at home. You'll see here's our artificial star in the center here. I'll put my pointer right there. So what you can do is you might have to lean back a little bit or move your chair back a little bit, but close one eye and hold up a finger so your fingertip is right near the star. Now your finger can't be close to your monitor, so move back from the monitor maybe 3 feet or something like that, and hold your finger up so it's pointing to that star on the screen right here. Now what you're going to do is switch eyes. Close your eye that you were looking with and open up your other eye. So go from your left eye to your right eye, or vice versa, and notice what happens. See how the star, and then you can blink back and forth between your two eyes. Notice how the star is apparently moving back and forth. So what's really going on here? Well, obviously the star here is not moving at all. It's stationary. But what's happening is we're seeing apparent motion due to an effect called parallax, which is the apparent change in position of an object due to the change in position of the observer. Since you're switching eyes from left to right, the angle of sight to this point here in the sky or on the screen changes, whether you're looking from your left eye to your right eye. And the distance between your two eyes is the baseline of the triangulation that we're doing here. So what astronomers figured out is that here's the sun and here's the Earth in its orbit around the sun. So what they do is they can choose this point right here and measure the angle to some star in the sky. And then 6 months later, when the Earth has gone around the sun and is over here, this star obviously is going to have a different line of sight angle depending on its distance to the Earth. And so our baseline here that astronomers are using is 2 astronomical units, because remember 1 AU is from the sun to the Earth. So this whole diameter of the orbit is 2 AU. So that's a very large baseline, which is good. So astronomers use this method and then they do the math, which, again, don't worry, we're not going to do that here in this course, but they can figure out and determine the distance to relatively nearby stars using this what's called trigonometric parallax. So let's take a look at some of the closest stars. The closest star system to our sun is Alpha Centauri, which is in the constellation of Centaurus, which is a southern constellation that's not visible from the northern latitudes where we live. But if you live south of the equator, you can see this fairly bright star. And so Alpha Centauri is 4.3 light years away. Now remember, a light year is almost 6 trillion miles. So it turns out that the closest star to us, the closest neighbor, is 25 trillion miles away. So the bad news here is that even our closest stellar neighbors are unreachable by our current technology. It would take thousands and thousands of years to send a spacecraft to even the closest star. Let's look at a couple others. There's one called Barnard's star, which is about 6 light years away. The brightest star in the sky is called Sirius, the dog star, and it's also relatively close. It's about 8.6 light years away. And then in the summer sky, there's 3 bright stars which form the so-called summer triangle. 2 of them are relatively close by. Altair is 17 light years, and Vega is 25 light years. But look at this one here. Deneb is 1,600 light years away. It's much farther away, and most of the stars in our galaxy are even much farther away than this. So what are the stars made out of? Well, the composition of stars is determined by analyzing the spectrum that the stars produce. So remember, this is that science called spectroscopy, which we looked at earlier in the course when we studied atoms. So using spectroscopy, scientists and astronomers were able to figure out the exact composition of stars. So it turns out that all stars in the universe, as far as we know, consists of at least 97% hydrogen and helium. The rest of the elements are the heavier elements. This is a list of the abundance of elements in our own sun. You can see that our sun is about 91% hydrogen and about 8.9% helium. So hydrogen and helium make up 99.9% of our sun's atoms, and the rest is all just a small trace of all the other elements, carbon, nitrogen, oxygen, neon, etc. They're all there in the sun, but in small amounts. So finally now we can get to classification of the stars. So there are roughly 200 billion stars just in our galaxy alone. And of course, there are hundreds of billions of other galaxies. So it seems like a futile and maybe impossible task to try to make sense of so many stars. But actually, it's not that bad. Just like biologists who classify living organisms, we can put stars in specific classes. And by using a classification scheme, we can make some sense out of the enormous numbers of stars. So what we're going to do is we're going to classify stars based on their physical properties. One of the properties that we're going to use to classify stars is called their luminosity. Luminosity is just a fancy word for brightness. So luminosity is a measure of how much energy the star puts out per second. And the units of luminosity, or L, are energy per unit time. So joules per second, and remember, a joule per second is called a watt. So luminosity is a measure of how bright the star is. For example, our sun has a luminosity of 4 times 10 to the 26th power watts. So think about, if you go to the hardware store and buy a light bulb. So if you want a really bright light bulb for your room or garage or something like that, you might choose a 100-watt light bulb. That's very bright. Well, our sun is a 4 times 10 to the 26th power watt light bulb. So this is a 4 with 26 zeros after it. All right, so needless to say, our sun is extremely powerful and produces a lot of energy. However, look at another star here called Capella. Capella has a luminosity of 4 times 10 to the 28th watts. Now, 10 to the 28th is 2 orders of magnitude, 2 powers of 10, higher than 10 to the 26th. So what this means is Capella is 100 times brighter than our sun. So if you were to place Capella somewhere in space, you would have to take 100 of our suns. This is 10 rows and 10 columns of our sun to equal the same amount of brightness as one Capella. So what makes some stars brighter than others? Well, there are just 2 factors that determine the luminosity of a star, and they are both shown in what is called the Stefan-Boltzmann law. The Stefan-Boltzmann law tells us that the luminosity or brightness of a star is equal to the product of 3 things here. Now the first thing here, this is the Greek letter sigma. That's just a constant. It's called the Stefan-Boltzmann constant. It's a number that doesn't change. So these are the 2 things that affect the brightness. One is A, which is the surface area of the star, and the other is T, which is the surface temperature of the star. So in other words, a bigger star is going to have more area and therefore will be brighter. It has more surface that's emitting light. So if we have 3 stars here that are all the same temperature, all right, they're 3 yellow stars, let's say, the big one here is going to be brighter than the small one here, just because of its larger surface area is giving off more light. Now the temperature also shows up here, and notice it's very sensitive to temperature because the temperature is raised to the 4th power. So what this tells us is that hotter stars are much brighter than cooler stars. So if we see 3 stars like this, a red, a yellow, and a blue. Well, remember in astronomy, red means the coolest star, and blue means the hottest star. So the brighter star here is going to be the blue one because of its higher temperature. So here's a little conceptual quiz to see if you can understand which star is brightest in each group. So for example, in question number 1 here, shown are 3 stars. So which one of these stars would be brightest? Well, the answer is C, because this star is largest. Now, what about question 2? Which of these 3 stars would be brightest? The answer here is star B, because B is blue, and remember, blue is the higher temperature. This is the hottest star that's shown between A, B, and C. For question 3, which of these 3 stars is going to be the brightest? Well, here the answer is A for sure, for 2 reasons. A is bigger than B and C, and A is also hotter than B and C because of its blue color. Now, what about the last one here? Which one of these 3 stars would appear the brightest? Well, this one we don't really have enough information. This one would depend. Obviously, A is the hottest star, which tends to make it bright, but C is the biggest star, which also makes it brighter. So we don't really know without actually plugging in numbers for the specific areas and specific temperatures, and we're not going to do that in this course. Don't worry about the details there. It would depend, which factor, bright, heat, temperature, or size, which one of those factors dominates here. So speaking of star brightnesses or luminosities, it's convenient to compare other stars' brightnesses or luminosities to our own sun's luminosity. So we said that our sun has a luminosity of 4 times 10 to the 26 watts. Well, instead of writing this out, this kind of big clumsy number, we're just going to call this amount of brightness 1 solar luminosity. So this L is for luminosity, and this symbol here, the circle with the dot in the center, that is the astronomical symbol for our sun. And it turns out that all the planets in our solar system have their own symbols. So this is the symbol for our sun. So for example, if a star is 20 times as bright or luminous as our sun, we would say its luminosity is 20 times the luminosity of our sun, or we could just say that its brightness is equal to 20, and what we imply here is that we're comparing it to the brightness of our sun. So for all known stars, the brightness of stars falls between this enormous range. 10 to the negative 5 means 100,000 times dimmer than our sun. Some stars are that dim, whereas other stars can be 10 to the 6th power, which is 1,000,000 times brighter than our sun. So we see a huge range in brightness between all of the stars in our galaxy, and our sun sort of fits somewhere in the middle. So the other property of stars that we're going to use to classify the star is actually the surface temperature of the star. Now, how can we measure the surface temperature of a star? Obviously, we can't, send a space probe with a thermometer and actually, reach one of the stars. Remember, the closest star is 25 trillion miles away. So instead, we can measure the temperature of a star precisely and indirectly by looking at its color and its spectrum. So without going into a lot of the details here, remember just the basic things is that red is cool and blue is hot. So in this star cluster here, we see this reddish star here would be relatively cool. This blazingly bright blue star here is hot, and then white stars or yellow stars are somewhere in the middle, would represent a medium temperature. Astronomers actually use a much more precise way of measuring stellar temperatures by inspecting the actual spectrum of the star. And we're not going to go into the details of that in this course, but I'll just tell you that we can very precisely determine the temperature of any star by looking at its spectrum. So Once we know the temperature, the surface temperature of a star, we can start to classify them into what are called spectral classes. And the spectral classes are listed here with the letters O, B, A, F, G, K, and M. Now, it's kind of too bad that these aren't in alphabetical order. The actual reason for these this kind of random ordering of letters has to do with history. And the early astronomers in the 1800s started coming up with this way of organizing the spectral classes. And at that time, they didn't know what we know today, so we're sort of stuck with these classes. But we're going to use these anyway as it's standard in astronomy. So what this means is the ones on top here, the type O spectral class, these are the hottest stars. They have surface temperatures somewhere in the order of 40,000 kelvins. The next class is B. And so notice I put O as blue, because remember, blue means hot in astronomy. B is still sort of a bluish star, maybe 20,000 kelvins. Next class is A at 10,000. And then we're starting to get, this is now the white and the yellow stars here. Here's class F, which we would call maybe a medium temperature star. And our sun is actually a class G star. And class G stars have temperatures somewhere in the 5,000 Kelvin range. And then after that, there's a class K, and finally the coolest class of stars are the type M stars. So those are the red stars, and they're somewhere on the order of 3,000 kelvins. So there's an easy way, I guess it's an easy way to remember these spectral classes. And so this is a mnemonic to remember the spectral sequence, and it's O, B, a fine girl or guy, kiss me. All right, so this is the O, B, A, F, G, K, M order of spectral classes of the stars. And these spectral classes are just a way of classifying the stars by their temperature. Remember, these are the hot stars on the left and the cooler stars on the right. Oh, be a fine girl, kiss me. So now we have enough information to organize the population of stars by their classification, by their spectral class, and by their brightness or their luminosity. And this was first done by two American astronomers named Hertzsprung and Russell. So the Hertzsprung-Russell diagram, which everyone just calls an HR diagram because that's much easier to say. By the way, here's Mr. H and here's Mr. R. What this is a diagram of where we're going to plot stars on this graph with brightness plotted versus surface temperature. So in this vertical axis right here, this is the luminosity of the star, or how bright it actually is. Now we have to be a little careful. This is not how bright it looks in the sky, because most of the stars are quite dim because they're so far away. This is the actual intrinsic brightness of how bright the star would look if we were right up next to it. So remember that everything is measured compared to our sun. So our sun has a brightness or a luminosity of 1. This up here, this is 10 to the second power. That's 100. So stars here are 100 times as bright. This is 10 to the fourth power. That's 10,000 times as bright. And then going down, we see that the stars get dimmer. 10 to the minus 2 is only 0.01, or 100 times dimmer. And so this scale is not linear. It's actually what's called logarithmic. It goes up as the powers of 10. What's plotted down here on the horizontal axis is the surface temperature of the star in kelvins, in absolute temperature. But what's kind of weird and quirky about the HR diagram is it plots hot temperatures on the left and cool temperatures on the right. So this is, a little different than you're used to drawing a graph, where your math teacher probably always told you to, you put 0 over here and the numbers get bigger as you go to the right. Well, astronomers always like to do things a little bit different, I guess. And so they made the HR diagram with the hottest stars over here on the left. So notice here are the spectral classes. O, B, a fine girl, kiss me. And they correspond to these temperatures shown down here. So let's just plot a couple stars and see how we would do this. So for our sun, remember our sun is a type G spectral class star. It has a surface temperature of about 5,800 degrees, which is about right here on our graph. And our sun, of course, has a brightness of 1 sun. So it is showing up right here to the right of 1. So there is our sun plotted on the HR diagram. Let's take another star and see where it belongs. So this is the star Vega. So Vega is a spectral class F star. It's hotter. It's around 10,000 degrees Fahrenheit for its surface temperature. Kelvins for its surface temperature. And Vega has a brightness of about 100 suns. So remember 100 on the scale, that's 10 squared. So that's why it's up here. So this is the HR diagram, how we are going to organize the stars according to brightness and surface temperature. So let's see what happens now when we put lots and lots of stars on this diagram. So here is the HR diagram showing thousands and thousands of stars plotted. Every little tiny dot on this diagram, and again, there are probably tens of thousands of dots, every dot represents a star. Here's our sun, for example. So again, remember on this HR diagram, this is relative brightness or luminosity compared to our sun, right? Our sun has a value of 1, so there it is. And then down here is the temperature, the surface temperature of the star in kelvins. And again, the spectral classes are sometimes shown on these diagrams, not always, but I put them here just to remind us. This is type O stars, B stars, A, F, G, K, and M, and those spectral classes, remember, have to do with temperatures. So what's the significant thing here is that when we plot stars on the HR diagram, we don't see that they are just randomly distributed everywhere on the diagram. They form distinct specific patterns, and these patterns are enormous clues as to the life and birth and death of stars. And we'll be exploring this more in this lecture and also the ones that follow this. But what we can see here right off the bat is there is a big dominant structure where most of the stars, in fact about 90% of all the stars fall on this diagonal stripe, which is called the main sequence. So the main sequence starts up here in the upper left-hand corner. These stars, remember, are hot because they're type O, and they're very bright, right? This is 1,000,000 times brighter than our sun. And then the main sequence swoops down across the HR diagram. Here's our sun. Notice our sun is a main sequence star, and it ends up down here with the type M stars, which are the coolest stars, around 3,000 kelvins. And notice they are also some of the dimmest stars. Their brightness is only something like 1/10,000th of the brightness of our sun. So let's now look at some of the other features of the HR diagram other than just the main sequence here. So notice there's quite a large population of stars up here, and if we follow this dotted line here, remember that this dotted line lines up with our sun, meaning any star that falls on this dotted line has the same temperature as our sun. However, some of these stars here are 100 times brighter than our sun. These stars here are 10,000 times brighter than our sun, and the stars way at the top here are 1,000,000 times brighter than our sun. So how can a star be that bright if it's not hotter than our sun? Well, remember there are two factors that make a star bright. One is the temperature, but that's not at play here because they have the same temperature as our sun. So the other factor, if you remember it, is the size of the star. So these stars up here must be larger. And in fact, they're called giant stars. These are stars that are huge compared to our sun. They are swollen stars that are basically towards the end of the star's life. And we'll talk about what makes a giant star later. Likewise, these stars down here, especially if we look at this group right here, they also have the same temperature as our sun. If we follow this dotted line right down here, it kind of clips these stars right here. And notice there's a whole sort of sequence of stars here. Well, these stars are these guys here have the same temperature as our sun, but notice they're about 100 times fainter. Now, why is that? Well, they must be smaller. In fact, they are. So these are called white dwarf stars, and we'll talk later about what makes a white dwarf star. So here is, again, the HR diagram with all of the populations of stars labeled. So the main sequence is this diagonal stripe going across the graph. The giants and supergiants are these populations of stars above the main sequence. And then the white dwarf stars is the population of stars below the main sequence. Speaking of the main sequence, if we were to pluck out a sample of each spectral class of star along the main sequence, so we have a type O star, a type B star, an A, an F, a G, a K, and an M, and if we laid them right next to each other like this, they would look something like this. So this is kind of an interesting diagram just to get a sense of what these various stars, how they compare to each other. So notice that the type O star, remember blue means hot, and they're also big. Okay, so these are the more massive, most massive stars on the main sequence. And then coming down the main sequence, we have the B, and then the A star is kind of a white color. F star here is starting to get kind of yellow. And then here, of course, is our type G star, which is our sun, is a spectral class G star. And then after that, there's a K and an M. And notice the little type M star is very small, and also it's very cool because of its red color, and that's why this little star is so dim compared to this big and hot type O star. This is another version of the HR diagram, which is kind of nice because this one's a little more graphic. It shows the stars with colors that correspond to their temperature in addition to sort of their relative sizes, although it's certainly not the scale. But what it shows here is along the main sequence, we have the cool, small, red type M stars. And you can see the spectral classes down here, O, B, fine, girl, kiss, meet. And so here are the red stars, and then going up the main sequence, we get to the K stars. Here are the G stars, including there's our sun right there. And then moving up, we get the type F and type A and type B, and now we're into the blue stars. These are the hot stars, the type O and type B stars. And then up above, we see the giant stars and the supergiant stars. Notice how large they are shown on this diagram compared to their cousins here on the main sequence. And then down here are the tiny little white dwarf stars. Another thing we can put on the HR diagram, which is sort of gives us a sense again of the size and mass of the star, is to actually write the mass of the star in terms of solar masses. So what that means is that our sun would have a number 1 for mass. It weighs 1 sun. So the smallest stars here, the type M stars, have a mass of only about 0.1, which means they're about 10 times smaller than our sun in terms of mass. But notice as we go up the main sequence, the numbers get larger and larger and larger. And so stars near the top of the main sequence actually can reach close to 100 solar masses, and we'll talk about that limit shortly. The other thing that we can talk about now is how long a star lives. And you would think that maybe these larger stars would live longer because they have more fuel. So what determines a star's life is how long it can burn its hydrogen fuel. And when I say burn, I have to be careful there. What we're talking about are nuclear fusion reactions. So it's often called nuclear fusion burning, but that's just sort of an analogy. It's not really a chemical. It has nothing to do with chemical burning with oxygen. It's nuclear reactions. So when a star runs out of hydrogen, it basically has run out of gas, okay, just like your car would run out of gas. So looking at these stars, we see large masses. That's like having a large gas tank. you might expect that these stars are going to live longer, but actually they don't. These stars up here live around 1 million years, which is very, very short. These stars are basically dying almost in their infancy. Our sun, for comparison, has a total lifetime of about 10 billion years. So our sun is only about halfway through its life. As we go farther down the main sequence to the lightweight stars, they can last trillions of years. Now, why is that? Well, even though these stars are really small, remember they are very dim and they're burning their fuel much more efficiently. They're burning their fuel so slowly that they will take many, many more times to run out of fuel compared to these big stars up here. So if we think of these stars like cars, these are like the big gas-guzzling SUVs with engines that have big gas tanks, but they're burning through their gas so fast that they run out of gas more quickly. This is like the little, economy Toyota Prius type car that has a tiny little gas tank, but it just has such a good fuel economy that it can go and go and go on the same tank of gas. So that's what determines the lifetime or the longevity of a star. So we saw in the previous diagram that the largest stars are somewhere around 100 times the mass of the sun. Anything larger than that, and they become unstable, and they just can't hold themselves together. There's too much energy being released. There's also a minimum limit for how small a star can get, and the minimum mass of a star is about 8% of the sun's mass. So this 0.08, which is 8%, times the mass of the sun. So what happens below this mass is the star is simply not hot enough in its core to start the thermonuclear fusion reactions. Remember, that's what powers a star, is nuclear fusion, fusing hydrogen into helium. So nuclear fusion requires core temperatures somewhere between 3 and 5 million kelvins. Our sun, for example, is around 15 million kelvins, so well above this. But the smallest stars, if we get below this temperature, fusion just doesn't happen. And the star then is not really a star at all. It's called something else. It's called a brown dwarf. It's a star that's too small to ignite. Its surface temperature is typically less than about 2,000 kelvins, and brown dwarfs are very dim because they're not giving off much light at all. They're mostly giving off heat, and they can be seen in the infrared. This is an image here of a brown dwarf star that's actually orbiting with its larger Big Brother star here. This is called a binary star system. So Big Brother here is a regular star, and this is the tiny little brown dwarf star. In fact, it's just a brown dwarf. I shouldn't call it a star at all because it's not. This is a Hubble Space Telescope image of two twin binary brown dwarfs. So again, these two objects here just don't have enough mass to get hot enough to ignite themselves like a real star. So that's what determines the lower limit of how small a star can be. And that, by the way, concludes this segment of the chapter. We'll talk next about how stars are formed and how they die in the next part of this chapter. I'll see you then.